Okay, we will start mass spectrometry today, isn't it?
Yeah, miss, we stopped here.
Yes, okay. Now, what is mass spectrometry? As we studied, maybe, I don't know if you remember or not, that in mass spectrometry, the molecule, our molecule is subjected to a high stream of highly energetic electrons, highly energetic electrons. And these electrons, when they strike the molecule, an electron will be ejected from this molecule, and the molecule will be transferred to a positive ion. It will form a positive ion. And this positive ion, when it moves through the mass spectrometer, it will be subjected to a magnetic field. And in the magnetic field, the ions are deflected in the magnetic field. I don't know if you remember such things or not. This is a magnetic field where the ions are going to be deflected inside the magnetic field, depending on two things, depending on their charge and depending on their mass. So the more the charge and the lighter the ion, it will be deflected more than the heavier mass or the smaller ion. So here, smaller ion and large mass. And this one will be deflected the higher charge and lower mass. So inside the spectrum, the mass spectrometer, the molecule is subjected to a highly energetic beams of electrons. When these electrons strike the molecule, they will eject an electron out of it, and a positive ion will be formed. And then this positive ion will go through the mass spectrometer, where it's going to be deflected by a magnetic field, depending on two things, depending on its charge and its mass. The higher the charge, of course, we don't have here charge except +1 and +2. So this is the higher charge, which is +2, and the lower mass will be deflected more than the smaller ion having a +1 charge, and the larger mass, they will be deflected less. And then they will enter the detector, where in the detector there will be the mass spectrogram drawn, and we will get certain peaks or certain lines that we are going to call them peaks. And of course, I'm going to explain afterwards what happens here. But I just wanted you to remember what we did before about mass spectrometer. Okay? Understand till here, Lara?
Yeah, I understood.
Okay. Now here, when the molecule is subjected to the electrons and an electron is ejected, it will form a positive ion. But this positive ion also can be more fragmented. It will be fragmented. It means that it's going to be broken down into simpler ions. After it is formed, then it's going to be fragmented into simpler ions. Every time we get a different ion, and each of these ions will also appear in the mass spectrogram. Every fragmented piece here will be in the form of positive ions, and each fragmented ion will have a characteristic peak here, depending on its molecular mass. Depending on the molecular mass of the ion, we will get a certain number of peaks. Now, the last peak here, we call it the molecular ion peak. We denote it by Mn positive. It means the molecular ion peak. And from the molecular ion peak, we get the molecular mass of the compound. So here, the last peak will show us the molecular mass of the compound, because we are drawing here mass over charge ratio against the percentage abundance. And the last peak here will show us the molecular mass of the ion, which is the bigger ion, the one at which only the molecule lost an electron and it formed a positive ion. This one will show us a peak, giving us its molecular mass. We call it the molecular ion peak. Sometimes we will find one of the peaks having a higher height than the others. It doesn't mean anything except that this ion is the most relevant one in our mass spectrometer. It is the one that is having a high number. That's why we got it as the highest peak. But only it shows here the mass over charge ratio. And since here in our study, we are going to consider only that molecules form only +1 ions. So all the peaks here corresponds to the molecular masses of the fragmented ions. Okay, Lara? Understand?
Yeah, Miss, I understand.
Okay. So here we have two types of mass spectrometers. We have low resolution mass spectrometer and we have high resolution mass spectrometer, as well as we have seen in case of proton NMR. So in the low resolution mass spectrometer, we will get, as you see here, a plot between the relative abundance percentage against the mass to charge ratio. You will see, of course, that we have different peaks here. And as I told you, that the last peak here is going to be called the molecular ion peak. This is the molecular ion peak. And from the molecular ion peak, from here, we get the molecular mass of the compound. So here, for example, it says that this is the mass spectrum of propanone. And propanone has this molecular formula. And so it has 3 carbon atoms, so 3 times 12 makes 36. It has 1 oxygen atom, so it's 16. And we have 6 hydrogen atoms. So altogether, they make 58. And that's why we will see that we have a peak here at 58, giving us the molecular mass of propanone. Then after that, propanone, this is, of course, we should write it in a positive ion form. You should write it in a positive ion form. And then this molecule is going to be fragmented. It means that it's going to be broken down into simpler ions. So maybe it's going to be broken here, resulting in a CH3 positive ion. And this has a molecular mass of 15. That's why you can see here a peak at 15. Now, it also can be broken from, so this is a CH3 positive, or else it can be broken in the C double bond O positive, this part. So if it gives us this ion, so we have 2 carbon atoms, 24 plus 3, we get plus 16 for the oxygen. So 7, this will be 2 and 2, it makes 43. So we got this peak. So this peak is for the 3H3 positive ion, and this is for the 3H3CO positive ion. Okay, we don't have any other probabilities. So these are the only probabilities that we can get from the fragmentation of propanone. That's why you can see the mass spectrum of propanone to be in this formula. Okay. So as we said here, either that propanone breaks down into a methyl free radical and CH3CO positive, because always the other part, when fragmentation takes place, one of the parts will be carrying a positive charge and the other will be carrying a free radical. So if the fragmentation happened in this part, so either we get a CH3 positive ion and the rest of the molecule will be in the form of a free radical, or else we get this part as the positive ion and CH3 as a free radical. And every positive ion will show us a peak in the mass spectrum. Okay.
Miss,
Yes.
what if we fragment it and like it was a big molecule and we had like, let's say 3 products or 3 parts? Which one would be the free radical, like one free radical and the rest
No,
are?
every time it's going to be only fragmented into 2 parts. One of them is going to be a positive ion and the other will be a free radical. It cannot be fragmented into 3 different parts, only 2 parts.
Okay, fine.
And of course, it depends upon the peak that will be shown. The peak that is going to be shown is the positive ion, and the rest, any other thing, will be a free radical, even if this happens. And even if, as you said, it will be fragmented to 3 parts, only one of them that carries the positive charge is going to show a peak in the mass spectrometer. But the others will be in the form of a free radical. Okay. Now,
okay.
let's look here for, this is ethanoic acid. If we look at the structure of ethanoic acid, it is CH3, C double bond O, OH. And so here, in the first part, this molecule as a whole is going to form the positive ion, from which we are going to get the molecular mass of ethanoic acid. If you calculate the molecular mass of ethanoic acid, 2 carbon atoms, 24, 2 oxygens, 32, and 4 hydrogens. So altogether we get 60. That's why we got here this peak at 60, which corresponds to the positive ion of the whole molecule, which we called it before the molecular ion peak. And then this molecule is going to be fragmented. As we said, either it's going to be broken here. So we get a CH3 positive, and this CH3 positive will show us a peak at 15, corresponding to 12 plus 3 makes 15. If it's broken from the other side, we get 1 carbon, 12, and 2 oxygens, 32, 1 hydrogen, 1. So altogether, it will make 45. That's why we got this peak at 45. It corresponds to COOH positive. We should write a positive ion. Now we got another peak at 43. So we are going to try, of course, 43 means that there is only 2 hydrogens less. But let us try this part. Let us try this part to see if it's 43 or not. So we have 2 carbons, we have 1 oxygen and 3 hydrogens. So yes, this is 43. So this means that the peak at 43 corresponds to CH3CO positive. So you will see they will show you other peaks as well. But we are not concerned by these other peaks. As long as he didn't write for us any numbers above the peaks, then we are not going to be concerned with them. Okay? We are only going to see the peaks that is written on them, the numbers. We are going to see which these peaks corresponds to which fragments, of course, in the form of positive ions. Okay.
Miss, and is it possible to take, for example, CH3COO, or is that not possible?
Yes, no, it's possible. You can get it. But as you see here, if we have a CH3COO positive, then it would be, I think it's going to be 59, because only 1 proton is removed. The whole molecule is 60. Yeah. But I can't see here any peak at 59, which means that we didn't get it. Okay, it depends upon the peaks you get.
Oh, okay.
Okay. Now, we call this the low resolution mass spectrum. Now, what is the high resolution mass spectrum? Sometimes when we get the molecular ion peak of a certain compound, we find that the molecular mass is, for example, here it's 60. So sometimes we find that more than one compound can have this molecular mass, because sometimes when we are preparing new compounds, we will not be certain that our compound that we want to prepare is prepared, but maybe another compound was prepared as well. So the molecular ion peak will show us the molecular mass of the compound. It could be of different molecules. So in order not to be confused about the molecular ion peak, whether it is from this compound or from that compound, if we calculated the molecular mass of two or more compounds, they will have the same molecular mass. So to distinguish between them, we are going to use what we call the high resolution mass spectrum. Now, as you see in the previous examples, when I calculated, for example, the molecular mass of, for example, ethanol, we used carbon as 12, we used hydrogen as 1 atomic masses, oxygen 16. But in the high resolution mass spectrometer, we are going to use exact relative atomic masses or relative isotopic masses, not 12, 1, 16, no. For example, here in hydrogen, the relative isotopic mass of hydrogen is not 1. It is 1.00782446. So in the high resolution, we have to use this value, not to calculate just 1 for hydrogen. Carbon, it's 12. But nitrogen, it's not 14. It's 14.003078. So we have to use this value. In oxygen, we have to use 15.9949. Of course, if he's asking you about the high resolution mass spectrometer, then he should give you these relative isotopic masses. You shouldn't just study them. They will give it to you. Okay. So for example, if we take an example here, if we have two molecules, like for example, C2H7N, this molecule, and that molecule, if we use the low resolution mass spectrometer, then for C2H7N, it's 24 plus 7 plus 14. So we get here, I think it's 11, 15, so it's 45. Now, if I calculate for CH3NO, so 1 carbon, 3 hydrogens, 1 nitrogen, 1 oxygen, so it's also 45. So both of them had this molecular mass, which is the 45. So which one of these molecules is present? So we are going to be confused because we don't know whether our formula is this one or that one. But if we used the high resolution mass spectra by using these masses instead of these masses, we can really find out which one of them is present. So if we calculate for C2H7N positive ion peak, we will find it to be 45.057846. And for the CH3NO positive, we'll find it to be 45.021462. So there is a difference here. So in the high resolution mass spectrum, it gives us more precise molecular masses. Instead of just giving us 45, it will give it to us using more decimal places. So from which we can determine whether our compound or our ion is in one form or in another. Okay. Understand, or do you have any question?
I understood this.
Okay. Right. There is something else that we have also to get benefit of, which is using what we call the M+1 peak. Now, what is the M+1 peak? Now, sometimes at our mass spectrometer, after our molecular ion peak is obtained, we find that there is a very small peak that is found here after just one unit. After just one unit after the molecular ion peak, we get a small peak here. After just one unit, is if our molecular mass is 60, we find that there is a peak at 61. We call it the M+1 peak. We call it the M+1 peak. And this peak doesn't mean that our molecular mass is 61. No, at the beginning it is 60. But you know that we said before that we have two isotopes of carbon. We have an isotope of carbon 12 and we have an isotope of carbon 13. And we said that the ratio between these percentages of the percentage abundance, this is 99% found, and this is only found in 1%. So there is a big difference between them. That's why difference in percentage. That's why most our mass spectrums, in most of them, we get only the molecular ion peak. But sometimes one of the carbon atoms in the molecule is a carbon 13 atom, not a carbon 12 isotope. And in that case, we get the molecular ion plus 1 peak. Okay. So we want to benefit from this peak. And the benefit is that we are going to use it to calculate how many number of carbon atoms do we have in our molecule. If we want to find out how many carbon atoms are present in our molecule, we are going to use a rule from which we can calculate the number of carbon atoms in our molecule. Sometimes they don't give you the molecular mass of the or the molecular formula of the compound, but they will give you the molecular ion peak, and they will give you the M+1 peak, and they will give you its percentage and say calculate the number of carbon atoms in the molecule. And from this information, other informations are going to be related to this information. So at the beginning, you have to find out how many carbon atoms are present in your molecule. And then after that, you are going to complete the rest of the problem. So how do we calculate the number of carbon atoms in a certain molecule from the molecular ion peak and its percentage abundance, and the M+1 peak and its percentage abundance? Now, as we said here, that the percentage abundance of carbon 12 to carbon 13 is 99% to 1%. And we are going to apply a rule that says that the number of carbon atoms in a molecule is equal to 100 over 1.1, as if this 100 is the 100% of the carbon 12, as if it is present in 100%, and 1.1 is the percentage of the carbon 13, times, we are going to do the opposite. We are going to put here the relative abundance of the M+1 ion peak divided by the abundance of the M positive peak. We are going to exchange their places. So the number of carbon atoms equal 100 divided by 1.1, and then times, we put up here, we put the percentage of the M+1 ion peak, and below we are going opposite to the 100, we are going to put the abundance of the metal positive ion peak, and from which we can calculate the number of carbon atoms. Okay, understand?
Miss, I just have one question. If they
Yes.
give us like a molecule, but you don't know the formula and you don't know the name, then and they show us the peak, if there's going to be an M+1 peak, like how will I know where's the actual molecular mass of the ion?
You are going to see that the last peaks you have is a peak which is already not very small, and after it by only 1 unit, there is a very small peak. Can you see it? It's very, very small. Can you see it here, the M+1 peak?
Yeah, I can see it.
Okay, that's what you are going to be given. Either you are going to be given the mass spectrum with this molecular ion peak, and after it by only 1 unit, you get a very, very small peak. And of course, they must give you the percentage of each in order to calculate the number of carbon atoms. Okay.
So Miss, you'll always hit like that, like a really tiny peak by 1 unit, and the one before it will be the one that's actually the...
Yes, yes.
Okay.
Okay. Now let's have examples. It says here an unknown compound has a molecular ion peak with a relative abundance of 54.5% and has a M+1 ion peak with a relative abundance of 3.6%. How many carbon atoms does the unknown compound contain? So we are going to apply the rule that n equals 100 over 1.1 times the abundance of the m plus 1 peak that is denoted here by 3.6 divided by the abundance of the metal ion peak, which was given here to be 54.5. So just you say that the number of carbon atoms equal 100 over 1.1 times 3.6 divided by 54.5, we get 6. So we have 6 carbon atoms. Okay. Understand? Okay. Now, sometimes also we have what we call the M plus 2 peak and the M plus 4 peak. When do we get the M plus 2 peak and the M plus 4 peaks? We get the M plus 2 peak whenever we have a chlorine atom inside our molecule. So we have the molecular ion peak that shows us that this is the molecular mass of the compound. We have seen that we have an M plus 1 peak from which we can calculate the number of carbon atoms in the molecule. But in other times, we have an M plus 2 peak. This means that we have a chlorine atom in our molecule. And if we have M plus 4 peak, this means that we have 2 chlorine atoms in our molecule. Okay. Now, as you know that also, if we have M plus 1, we can have a bromine atom. And here we have 2 bromine atoms. Either we have a chlorine or a bromine atom. Now, we know that for chlorine, it has 2 isotopes, chlorine 35 and chlorine 37. And the percentage is that the chlorine 35 is having a 75% relative abundance or percentage abundance, and the chlorine 37 is only 25%. And also we have 2 isotopes of bromine, 81 and 79. Each of them is 50% each. So if we have only 1 chlorine atom or 1 bromine atom per molecule, then in the molecule, we are going to have an M plus 2 peak. And if the M plus 2 peak is having a height that is 1/3 the height of the molecular ion peak, this means that we are having a chlorine atom. But if we are having the same height, yani if we are having like that, if this is the molecular ion peak, and after 2 units, we got another peak that is only 1/3 the one before it. So this is the molecular ion peak, and this is the M plus 2 peak. And we will find that the height between the molecular ion peak and the M plus 2 peak is 3:1. This means that we are having a chlorine atom inside our molecule. But if the ratio between them is 1:1, between the molecular ion peak and the other one that comes after it by 2 units, we find that both are having the same height. This means that we have a bromine atom in our molecule. Why? Why does this happen? For example, if you have a CH3Cl molecule, for example, then this chlorine could either be chlorine 35 or chlorine 37. And we know that the percentages are 75% and 25%. So you will see that at the beginning, you will get the molecular ion peak of the molecule. The molecular ion peak, its molecular mass will be 12 carbon, 3 hydrogen, and 1 chlorine, 35.5. So you will get your, 35 only. This is the isotope 35. So here we get our molecular ion peak at 50. 5 plus 3, 8 plus 2, 10. So we get it at 50. And then after just 2 units, you are going to get another one, but it's 1/3 its value at 52. What is this 52? It is if we replace, if one of these chlorine atoms was replaced by a chlorine 37. So if it is replaced by a chlorine 37, this is chlorine 35. So we will get this molecule having the isotope chlorine 37. So its molecular mass, if we calculate it, is going to be 52. And since the ratio between chlorine 35 and chlorine 37 is 3:1, the ratio here is 3:1. So this means that we are going to have these heights in the ratio of 3:1. Okay, understand?
Yeah, okay, Miss. And Miss, when we calculate the molecular mass, when do we know when to use those accurate molecular masses?
They will tell you. They will tell
Oh,
you in the high resolution or in the low resolution. They are going to tell you.
okay.
Okay. And if we have a bromine atom instead of chlorine, then as we said, bromine has 2 isotopes, bromine 79 and bromine 81. And both are having the same percentage. It means they are present in the ratio 1:1. That's why if you get in your mass spectrum, if you get 2 peaks, the difference between them is 2 units, and both of them are having the same height. This means that you are having a bromine atom in your molecule. So you will get the first one at carbon 12, hydrogens 3, and bromine 79. So you get it at 94. And then you are going to get another one at 96, corresponding to the presence of bromine 81 instead of bromine 79. But both peaks are having the same height. So here we can differentiate between whether we are having a chlorine atom or we are having a bromine atom in our molecule. Because if we are having a chlorine atom, we get an M+2 peak, but with the ratio 3:1 in between the molecular ion peak and the M+2 peak. And if we have a bromine atom, the ratio will be 1:1. Okay. Understand, or shall I repeat it?
Understood, Miss.
Okay. Okay, so here, as you see here, if we are having a molecule like that, no, this is 2. Here, if we are having this molecule, or the same as I told you, so we don't have any other example. Now, what if we have 2 chlorine atoms or 2 bromine atoms instead of 1? If you are having 2 chlorine atoms or 2 bromine atoms, for example, if we are having this molecule, CH2Cl2. So here we are going to have an M peak, an M+2 peak, and we are going to have an M+4 peak as well. We have 3 peaks, the M peak, the M+2 peak, and the M+4 peak. Okay, so the M peak here is when both chlorine atoms are of the isotope 35. If we are having this molecule, CH2Cl2, then the molecular ion peak will be observed for the molecule when both chlorine atoms are 35. So we get this M peak. The M+2 peak is when one of the chlorine atoms is 35 and the other 37. Of course, we have to say that also either this is the one that is 37 and the other is 35, but both will have the M+2 peak. Or if both chlorine atoms are 37, we get the M+1 peak. and we will get them in the ratio of 9 to 6 to 1. We did this before, the 9 to 6 to 1 in case in the AS, when we are having only a chlorine molecule. You remember this, or shall I give it to you in more details? Why do we get this ratio, 9 to 6 to 1?
Miss, I don't remember.
Okay. In AS, we said that if we have a simple molecule like chlorine, and this of course will apply also to our compound here, but I'm going to explain it first for the simple chlorine element. It's formed from 2 chlorine atoms, and as we said, we have 2 isotopes of chlorine. It's 35 and 30 chlorine 37, and they are in the ratio 3 to 1, as we said. And the mass of the total mass of the ratios, or the total ratio, is 4. 3 plus 1 makes 4. And this means that chlorine 35 is present in the probability of 3 over 4, and chlorine 37, 1 over 4 of the total chlorine atoms. So if chlorine molecule is formed, it could either be formed from both isotopes, chlorine 35, and so we get chlorine molecule 70. Okay, so we will get in our spectrum a peak at 70, which corresponds to the chlorine Cl2, where each of the chlorine atoms is 35, or else we have one of the chlorine atoms is 35 and the other is 37. So we get another peak at 72. So here also we get a peak at 72. This is 72. Or both isotopes are chlorine 37. So we get the chlorine molecule, chlorine 74, and we get a peak here at 74. And we will find that the ratio between the 70 to the 72 to the 74 is 9 to 6 to 1. This is 9 to 6 to 1. The heights are in this ratio, 9 to 6 to 1. Why the ratio is in that form? Now, we say that the first probability that we have that both chlorine atoms are 35. And this means that the probability of their formation is 3 over 4 times 3 over 4. So we get it as 9 over 16. Either that the first one is 35, the probability will be 3 over 4 times that the second is 35. Also, we multiplied by 3 over 4, we get 9 over 16. In the second case, we have the first chlorine 35, so it's the probability of its formation is 3 over 4, and the second is chlorine 37, 1 over 4. But also we have another probability that the first one is the one to be 37 and the second the one to be 35. In probability, we do that. We say either the first is 35, the second 37, or else that the first was 37 and the second is 35. So we multiply it, we add plus 1 over 4 times 3 over 4, and here we get 6 over 16. If we add them together, 3 over 4 plus 3 over 4, we get 6 over 16. 3 over 16 plus 3 over 16. Now, the third probability is that both chlorine atoms should be 37. So 1 over 4 times 1 over 4, this makes 1 over 16. Understand, Laura?
Yes, Miss, I understand.
Okay, and this means that if we get them in the form of a ratio, and this 16 will be cancelled, so the ratio will be 9 to 6 to 1. Okay, so it's the same here. It's the same here if we have a molecule, an organic molecule, CH2, Cl2, then maybe both its chlorine atoms are chlorine 35, or else one of them is 35 and the other is 37, or both chlorine atoms are in the ratio, are in the isotope of chlorine 37. And this means that here we are going to get our molecular mass to be carbon 12 plus 2, 14, 14 plus 70. We get a peak at 84. We will get a peak at 84, corresponding to this ion. Or we get, sorry, not this one, this ion, the CH2, Cl2, both are 35. Or we get here for the other one is going to be more than the first one by 2. So after 2, we get another peak at 86, corresponding to this ion. And the third is that we are going to get at 88, we are going to get this, the peak corresponding to this ion. So we get 3 peaks, M peak, M plus 2 peak, and M plus 4 peak, corresponding to these 3 species, 3 ions. And the ratio is the same as we said in case of Cl2. It will be in the ratio of 9 to 6 to 1, the same. Okay.
Miss,
So-
the first peak,
Yes.
the first peak with the M, does it mean that this molecule, like it originally has 84, the molar mass is 84?
Yes. All these are molar masses. I'm adding these atomic masses together. 35 plus 12 plus 2 plus 35. We get 84. All these are molecular masses of different species.
This
Of
is
different
because
ions.
when we use, we usually use 35.5 for Cl.
Yes, but now we are going to consider, this is another thing that we have to consider. We don't have in mass spectrum, we don't have points. We have all of them are actual numbers or integers. Okay, we have whole numbers. We don't have in mass spectrometer, we don't have a point.
Yeah, fine. Okay, I got
All
it.
the numbers are whole numbers. They are not having any decimals or any fractions. That's why we have to consider here the isotopes, the different isotopes.
Okay, Miss.
Because when we say 35.5, it is the average or the mean mass of chlorine 35 and chlorine 37, and depending on their percentage abundance, isn't it?
Yeah.
And when we are calculating chlorine, having the atomic mass chlorine 35.5, from where does this come from? It comes because we have chlorine 35 and we have chlorine 37. This is present in 75%. This is present in 25%. So we say that the relative atomic mass of chlorine, the average relative atomic mass is 35 times 37 plus 37 times 25 divided by 100, isn't it? This makes 35.5. That's why this is written in our periodic table, because they took the average of these 2 isotopes, depending on their relative atomic masses, depending on their masses and depending on their percentage abundance. But in mass spectrum, we do not consider them together as a whole entity, but we will consider every isotope alone. Understand?
Yes, I got it.
Okay. Now for bromine, in case of bromine, we are going to do the same, but bromine has 2 isotopes, bromine 79 and bromine 81, and both are present in 50%. It means that they are present in a 1-to-1 ratio, and the sum of these 2 ratios is 2. It means that the probability of the first one is half, and the second is also half. So if I have Br79CH2, Br79, then we are going to get the molecular ion peak at 79 times 2 makes 158 plus carbon 12 and 2 hydrogens. So we get 172. So we are going to get our molecular ion peak at 172. I'm just adding all the atomic masses together. Okay. And if we are having one of the isotopes is bromine 79, but the other is bromine 81, this means that we are going to have another molecular ion peak in 174. 174. And if we are having both bromine atoms 81, we are going to have a molecular ion peak at 176. But we will find that the ratio here is 1 to 2 to 1. Why is the ratio 1 to 2 to 1? It's the same as what we did in case of chlorine. In case of bromine, if both bromine atoms are of the isotopes 79, this means that the probability is half times half. This makes 1/4. Okay. If the probability is one of them 79 and the other is 81, then we have half times half plus we have maybe the first one is the 81 and the second is the 79. So also we have half times half. So we get 2/4. Or the third probability that both of them are 81. So it will be half times half. And this makes 1/4. So the ratio is 1/4 to 2/4 to 1/4. So the ratio is 1 to 2 to 1. Understand, Lara?
Yes, I understand.
Okay. So here, if in our spectrum, we get 3 peaks at M plus 2, and M plus 4, this means that either we are having 2 chlorine atoms in our molecule or 2 bromine atoms in our molecule. And depending on the ratio between the peaks, this is 112, this is 114, and for example, this is 116. If the ratio between the peaks is 9 to 6 to 1, this means that we are having 2 chlorine atoms in our molecule. But if the ratio is just 1 to 2 to 1, we have also 3 peaks at the end. One of them, the molecular ion peak, and the other is M plus 2, the third is M plus 4. But in the ratio 1 to 2 to 1, this means that we are having 2 bromine atoms in our molecule. Okay. Do you have any question here?
No, miss, I don't.
Okay. Now, now we are going to find out what are the applications of the mass spectrometer. Now, nowadays, we studied before in the last lesson, we have studied the GLC, which is the gas liquid chromatography, and the HPLC, the high performance liquid chromatography. We have studied them, and we have seen that both of them use retention times in order to find out what are the different molecules or the different compounds that are present in our mixture. We had a mixture, for example, A, B, and C, all present in a mixture. And so by using either GLC or HPLC, we can find out that we have different peaks by retention time. We have different peaks that we get. And from the number of peaks, we can determine how many components are present in our mixture. And we said from the area under the peak, we can determine the concentration of each species inside this, the concentration of each species inside this mixture. Okay, but nowadays, in order to be more certain about our compounds A, B, and C, because maybe two compounds could have the same retention time. Maybe A was not A, it was two other compounds, A and another compound D, for example. But both of them had the same retention time. So how can we differentiate between them? So in order to be certain that our compound is A and not D, or else D and not A, then they connect a mass spectrometer to the GLC or the HPLC. They connected. Then after every species in the mixture comes out from the GLC or the HPLC, at once it enters the mass spectrometer, where its molecule is going to be fragmented. Of course, we are going to be given its molecular mass, and the molecule itself will be fragmented to get the different peaks inside the mass spectrometer to make us certain that this compound is, yes, it is C, not any other compound. Understand what I mean?
Yes.
Okay. So here, for example, if you see here, after our compounds come out from the GLC or the HPLC, it enters the mass spectrometer. Now, this is the retention time by which this is the retention time that our compound came out from the GLC or from the HPLC. The retention time was 9 minutes, for example, for a certain compound. So at once, when as soon as it come out from the GLC, for example, it enters the mass spectrometer. So its retention time was 9, but in the mass spectrometer, it's going to be fragmented to the mass overcharge ratio of the different peaks, together with the percentage relative abundance. And by analyzing these peaks, we are now certain that our compound that came out at the retention time, for example, 9, has this molecular formula. Depending on its molecular ion peak, the last peak that we get in the mass spectrum gives us the molecular ion peak from which we can calculate the molecular mass of the compound. And from the different fragments, we now are sure that our compound is in this molecular formula. Okay, or in this structure, I mean.
Miss, here you said we look at the last peak, but what I get confused at is like, what if the last peak is the M+1 or the M+2?
As I told you, if you have a last peak and then you have only one very, very small peak after it by only 1 unit, then this means that this is an M+1 peak. Okay. But if you get 2 other peaks after the last one, you will find that there is a peak, and after it by 2 units, you get another peak, and after 2 units, you get a third peak in the ratio 9:6:1. This means that you are having 2 chlorine atoms in your molecule. If you have only the molecular ion peak, and after just 2 minutes, you got another peak. After 2 units, you get another peak in the ratio 3:1. This means that you are having only 1 chlorine atom. Okay. If you are having a molecular ion peak, and after it by 2, you got 2 units, you got another peak that has the same height as the first one. This means you are having 1 bromine atom in your molecule. If you are having a molecular ion peak, and after 2, you got After 2 units, you got one of them, which is double the first. After another 2 units, you got a peak like that, then you are having 2 bromine atoms. And of course, they are going to give you something to show you that this compound contains a chlorine atom or 2 or whatever. They are going to give you hints. They are going to give you information. And from this information, you are going to find out the molecular structure of your compound.
Miss, and when we look at the 9 to 6 to 1, for example, and they ask what is the molecular mass or something, do we look at the 9 ratio 1 because it's the M peak?
Yes, you look at the 9 only.
Okay.
Okay. Now, in what areas do we use GLC that is connected to an MS, mass spectrometer? There are different, of course, areas. We can use it in forensic science in order to analyze a sample of someone, for example, who took pills in order to suicide. So they are going to analyze the pills that they have found inside him and see what compound did he take in order to suicide, or sometimes someone kills another in a crime, and so they get a sample out of his blood, the sample of blood of the criminal, and they analyze it to find out who made this crime. So this is forensic science. Or else they use it in environmental monitoring of pollutants by analyzing air samples or water samples or ground samples. They can find out what pollutants are present using the GLC-MS. They can take samples of drugs to test them in sport, when we have athletes that are getting in a race, or sometimes horse races. Sometimes they give the athletes, they give them pills that will make them having more activities and can run faster. So before the athletes go into a race, they take urine samples from them and tested by GLC-MS in order to find out whether they have taken certain pills in order to have more activity. In geological and archaeological dating, to analyze the soil and find out, for example, this rock. Geological means that they analyze a rock and see what are the different components or different compounds that are found in this rock, and from which they can determine its age. Archaeological dating, the same. It means dating of a very old tree, or, for example, they found woods that were used by man from millions of years ago. From where do they know this dating? They can use this method. Airport securities also. So these different areas, in these different areas, we can use GLC followed by MS in order to find out the different compounds that are found in this. Okay. Also, they have used mass spectrometry by taking samples of rocks on Mars in 2005, and they analyzed it to find out what are the composition of the rocks in Mars. Okay. Also, we can use this mass spectrometry to help in medical research in order to, for example, if we have a protein and they want to find out the structure of this protein, from which amino acids is it formed, then they are going to analyze it using mass spectrometry. They are going to hydrolyze it first and then use the mass spectrometry in order to find out the components or the different amino acids that formed these proteins. Okay. They said that this is 2928. This is the mass spectrum of a peptide that consists of 5 amino acids. And from the molecular ion peak, they deduced the molecular mass of the peptide, which corresponds to this molecular formula, C28H37 and 507. And of course, they didn't give us the fragmentation, but from the fragmentation, we can determine which amino acids formed this peptide, polypeptide. Okay. Understand, or do you have any question?
Miss, what's soft ionization?
Where is this soft ionization?
I don't know if it's needed, but it's in figure 29.28. Like it's written in the
No,
last.
we don't study. He said that the mass spectrum of leucine, a peptide made up of 5 amino acids, it has been charged by adding a proton instead of by ionization by high energy electrons. They put a hydrogen positive ion to the molecule to get it in the form of a positive ion instead of subjecting it to a high stream of highly energetic electrons. In order to have a positive ion, instead of subjecting it to forming a positive ion by subjecting it to high energetic electrons, where an electron is ejected and the molecule forms a positive ion. Instead of this method, they used another method that they charged the molecule with a hydrogen ion. So this method is known as the soft ionization method. We don't study it. Understand?
Oh, okay, fine.
Yeah,
Got
this
it.
is another method in order to get our compound in the form of a positive ion.
Yeah, okay.
Okay, do you have any question in this chapter?
Miss, I have only one question regarding the chapter.
Yes.
It's in the part about identifying OH and NH signal. Can you just repeat that part?
The NMR?
Yeah, it's in the NMR. It's identifying the OH or NH signal.
OH or NH signal? You mean
Yeah, Miss,
the part where we use the deuterated oxide?
yeah, Miss, can you just repeat it like quickly?
Yes. We said that in both OH, if we have an OH or an NH in our molecule, then this means that we are going to have only a single peak. We don't have a splitted peak. Why don't, this is the first thing. Why do we have only a single peak and not a splitted peak that corresponds to what is neighboring to it? This is because we said that in presence of water, we will find that there will be an exchange, a rapid exchange. There will be a rapid exchange between the hydrogen that is present in our molecule and the hydrogen that is present in water. They exchange together rapidly. It means that if we have an alcohol, then it will form OH plus HOH. It means that one of these hydrogens was replaced by the hydrogen in the alcohol or replaced by the hydrogen in the NH molecule. And this exchange happens very rapidly. And that's why this hydrogen will not be splitted by others because it is exchanging its place all the time. So it's not affected by its neighbors. You understand this part?
Yeah, okay.
Okay, this is the first thing. The second thing is that we said that if we are doing our proton NMR spectrum, so for both the OH and the NH, we get a peak corresponding to this OH or NH. If we want to make sure that this peak is for an OH group or an NH group and not a CH1, if we want to make sure that our peak is an OH peak or an NH peak, depending on our molecule, of course, and it is not a CH1, so we are going to do our NMR spectrum normally, and then we are going to repeat the NMR spectrum in what we call deuterated oxide. What is deuterated oxide? It is water, but instead of putting hydrogen, they use the isotope, which is deuterium of hydrogen. Hydrogen is 1, 1. deuterium is 1, 2. This is deuterium. And in deuterium, as we have an even number of nucleons, we have a proton and a neutron, so we have an even number of nucleons, then it will not absorb in the NMR. We said that only atoms that have an odd number of neutrons or protons are going to absorb in the NMR spectrum. But those that are even numbers or have even numbers, they are not going to absorb in the NMR spectrum. Okay. So when we repeat the NMR in deuterated oxide, and since deuterium does not absorb, so during this exchange that we talked about, then the H will be substituted by a deuterium. During this exchange that happens between water and the OH, and now it's deuterium oxide with the OH, the hydrogen will be substituted by a deuterium. And deuterium does not have an NMR peak. That's why repeating it in deuterated oxide, you will not get this peak, because the deuterium doesn't absorb in NMR spectroscopy.
Okay, fine. And I got it. And Miss, also when we have, for example, CH3, CH2OH, for example. And here the OH, it doesn't have any, like it's not related. It doesn't depend on the other carbons or something, right?
Yes.
So for OH, you would have a single peak.
Yes.
And for CH3, since it has a neighboring hydrogen,
Yes.
It has two neighboring hydrogens, so it would have 2 + 1, so 3. So it would be
Yes.
split into 3.
Yes.
And then for CH2, it has 3, so it's 4
Yes.
for CH2.
Yes.
Oh, okay, fine. That's it.
And this will not be splitted because, as I told you, it exchange its place with the water that is present in the solvent.
So, and Miss, how do you draw, like, if you want to draw the graph, how would you put the 4 and the 3 and the single peak?
You mean the NMR spectrum?
Yes.
How do you show splitting?
Like, how would you draw it? How would you draw it if you had what I said, the triplet and the quartet and the singlet?
Like this. Either you of course you are not going to draw it in this way, but you are going to put lines beside each other. You see here, this is splitted to 4 and this is splitted to 3. So you don't have to make peaks like that. Either you make peaks or else you can put lines that are in the ratio to 1 to 3 to 1, and here 1 to 2 to 2 to 1.
And Miss, if we have like CH3, when we said it was bonded to 2 hydrogens, so it became a triplet peak. Here, in this case, the triplet peak, we put above it 3H.
Yes.
Because we have CH3, right?
Yes. Yes.
Okay, fine. Got it.
Okay. Any other question?
No, Miss.
Okay. Now, you said that you want the transition metal chapter?
Yes, please, Miss.
Okay. Okay.